And that will give you how the variable x is varied with respect to time. Okay. So now in this case, how we can invert this excess into a time domain? The first step is you can have a partial fraction from this particular equation excess, isn't it? So in this case, you can see that the p of s is a polynomial. First, you have to find out the roots of polynomial p of s, and with respect to the roots of polynomial p of s, you have to do the partial fraction. Let's assume that p of s are having n roots r1, r2 all the way to rn, and then we can represent this equation as c1 divided by r1s, c2 divided by r2s, and that summation goes all the way to cn divided by rns. Isn't it? Once we have obtained this, here you can see that r1s, r2s, rns, these are also the function of s, but you can invert these functions easily into time domain. Easily. Okay, and that is the reason why we have represented this excess in terms of the individual partial fractions. So once we have obtained this, then we can obtain the inverse Laplace transform x of t given as inverse Laplace transform of each of these terms, and we can add them, and that will be the output in time. This is what we have seen in the last class. We said there are three important cases possible, isn't it? First important case is when all the roots are real and distinct. When all the roots are real and distinct. What roots? R1, R2, Rn. These are the roots of polynomial p of s. If all the roots of polynomial p of s are real and distinct, in that case what we get is, in that case we get the exponential response. This is what we have seen in the last class. Whenever all the roots of polynomial p of s are real and distinct, we get exponential response. Exponential response means either the variable will increase and then become constant, or it will decrease and become zero, isn't it? You will not have any fluctuation. When we say the exponential response, that is what the insights we get. Okay. The second case was when the roots of the polynomial p of s are imaginary. So imaginary roots always occurs in conjugate pairs. So you can see in this case the order is 2. So you will be having two imaginary roots. With these imaginary roots, typically what we get is the output response is periodic in nature. Output response is periodic in nature. What it means is the variable, output variable is going to fluctuate. Not going to go like exponential increase or exponential decrease. Okay. So qualitative behavior of how your output variable is going to vary with respect to time, you can find out from the nature of the roots. If the nature of the roots are real and distinct, in that case the qualitative response of your output is going to be exponential increase or exponential decrease. But if the roots are imaginary, in that case the response is going to be oscillatory. Okay. So these are the two cases we have seen in the last class. Now let's look at third important case, and this case is also important primarily because when we will look at the stability of the control system, you will see why this particular case is important. Okay. Now the third case is when we are having multiple roots. So again take the example, x of s is given as qs by p of s, and let's take that this s of s is given as 1 upon s plus 1 cube plus s plus 1 cube into s plus 2. So there are 4 roots are there, isn't it? Out of these 4 roots, 3 roots are exactly same. So we are having a multiple root problem here. You can see that here s equals to minus 1. There are 3 such roots are there. So p1, p2, p3 are minus 1 and p4 is minus 2. Okay. So denominator p of s is having 4 roots. Out of the 4 roots, 3 roots are same. 3 roots are exactly same. Now how we can apply the procedure of inverse Laplace transform in this case? Again we have to find out the partial fractions. But finding the partial fractions is not straightforward in this case. Okay. It is not straightforward. Let's say if you represent the partial fractions like C1 divided by S plus 1, C2 divided by S plus 1, C3 divided by S plus 1, and then C4 divided by S plus 2. This is the usual way we have done in the last example, isn't it? This is what we have done. See, there are three roots. Corresponding to each root, we have taken a partial fraction. C1 divided by S minus 1 plus C2 divided by S plus 1 plus C3 divided by S minus 1. This is what we have done. But if you follow the same procedure, you will get stuck. You will not be able to find out the coefficients C1, C2, C3 when you are having a multiple roots. Okay. So this is the case with multiple roots. So in this case, the partial fractions are taken in a slightly different way compared to what we have seen when we are having real and distinct roots. In this case, we are not having distinct roots. In this case, we are having multiple roots. So for multiple roots case, how the partial fractions are represented? C1 divided by S plus 1, that is the first partial fraction. Second partial fraction is C2 divided by S plus 1 square. And the third partial fraction is C3 divided by S plus 1 cube. And there is another distinct root which is S plus 2, so that is taken as C4 divided by S plus 2. Okay. Are you able to see what is the difference? Here you can see that we have taken C1 divided by S plus 1, C2 divided by S plus 1 square plus C3 divided by S plus 1 cube. This is slightly different compared to what we have done earlier. Earlier we have taken partial fractions with respect to each of these roots, because all the roots in this case were distinct, isn't it? But the third case in which we are not having the distinct roots, instead of having the distinct roots, we are having multiple roots. Okay, and that is why we have taken slightly in a different way. So partial fractions are taken in a slightly in a different way, because if you don't do like this, you will not be able to find out constants even C2. You will not be able to find out. Okay. So once we have represented your equation like this, then you can invert it into time domain easily. What will be the inverse Laplace transform of first term? That will be C1 e raised to the power minus t. What will be the inverse Laplace transform of second term? Second term is having denominator s plus 1 square. When we get s plus 1 square, whenever we are having a ramp input, isn't it? Remember that? I can go back. So when we get a square term, t is there, and whenever t square is there, 2 divided by s cube, isn't it? Correct? Isn't it? So this is what the term we are getting, isn't it? This is what the term we are getting. S plus 1 square. So what will be the inverse Laplace transform? T into e raised to the power minus t. Isn't it? That is what we are going to get. Correct? So same thing is written here. See, the inverse Laplace transform of this term is C2 into t raised to the power t into e raised to the power minus t. Third term, there is a cube here, isn't it? So what we have usually t and e raised to the power alpha t, what we have? N factorial divided by s plus a raised to the power n plus 1. That is what we get the inverse Laplace transform, isn't it? That is what we get the Laplace transform. So in this case, the inverse Laplace transform of this will be what? T square divided by 2. Why? This 2 is coming from 2 factorial. Okay. So C3 divided by 2, T square e raised to the power minus t, and the last term will be C4 e raised to the power minus 2. So this is the inverse Laplace transform of the entire term. Now we have to find out C1, C2, C3 and C4. How we can find out? So easier is to find out C4. Why? Because it's not a multiple root. It's a distinct root. So we can follow the same procedure what we have done earlier. We can multiply this entire equation by s plus 2 and then put s equals to minus 2. You will get directly C4. So that is what they have done here. If you multiply s plus 2 to this entire equation, this s plus 2 will get cancelled out with this s plus 2, and on the right hand side C4 will be there. All other terms will have s plus 2. So if I put s equals to minus 2, all these terms are going to become 0, and right hand side I am going to get only C4. So C4 comes out to be in this case minus. C4 comes out to be minus. Okay. Now the remaining terms are C1, C2, C3. These three terms are corresponding to multiples. Out of these three terms, you will see that finding C3 is easy. Finding C3 is easy. Why? You can use the same method of partial fraction and you can find out C3. You can multiply this entire equation by s plus 1 cube and then put s equal to minus 1. You will get C3 directly. Okay. So that is what we have done here. We have multiplied this entire equation by s plus 1 cube, and you can see that only C3 is coming here. All other terms are having s plus 1 cube in the numerator, and if you put s equals to minus 1, what will happen? All these terms are going to become 0 on the right hand side. Only C3 will be remaining on the right hand side, and left hand side this s plus 1 cube will get cancelled out with this denominator s plus 1 cube. So only term remaining here on the left hand side will be 1 upon s plus 2, and we can put s equals to minus 1 here. So if I put s equals to minus 1, what I am going to get? C3 comes out to be 1 directly. Okay. Now challenge here is to find out C1 and C2. Finding C1 and C2 is not direct. In order to find out C1 and C2, what we have to do is, first we have to differentiate this equation 3 with respect to s. If you differentiate this equation 3 with respect to s, what you are going to get? Remember, this s plus 1 cube is cancelled out here. So only term remaining is s plus 2, 1 upon s plus 2. So if I differentiate this particular term, what I am going to get? I am going to get minus 1 upon s plus 2 square. Okay. And what will be the differentiation of right hand side? Right hand side, you can see that this term will become 0 because derivative of the constant term is 0. So this C3 will become 0. And if you look at the other term, this first term is s plus 1 square you will be having in the numerator. So derivative of that will be 2C1 s plus 1. This second term, since this 2 will cancel out with 2 here, so the only term remaining will be C2 s plus 1, and derivative of C2 s plus 1 will be just C2, isn't it? So we will get just C2 term here, isn't it? And this last term, here s plus 1 cube is there in the numerator and s plus 2 is in the denominator. You have to find out the derivative of this term, isn't it? It is kind of finding the derivative of u by v, isn't it? So derivative of this entire term is written here. Even if you don't know how to find out the derivative of this term, it is doesn't matter. Why? Because anyway the numerator will have s plus 1 term throughout. And if you put s equals to minus 1, this entire term is going to become 0. That is what is happening here. You can see if I put s equals to minus 1, remember we are putting s equals to minus 1 here. If you put s equals to minus 1 here, this entire term becomes 0. S equals to minus 1, if I put it, this term also becomes 0. The only term remaining on the right hand side is C2. If you put s equals to minus 1 here, minus 1 plus 2, that becomes plus 1, and minus I is here, isn't it? So C2 comes out to be minus. Right. Then the last term remaining is C1. So now again we start with this equation number 4. Again we can differentiate this equation with respect to s, and if we differentiate this particular equation with respect to s, what we get is this left hand side will become 2 divided by s plus 2 cube. Right hand side, here the derivative of this term is going to be 2C1. This derivative is going to become 0. This will have a complicated derivative, it doesn't matter. If you put s equals to minus 1, this last term is also going to become 0. So only term remaining on the right hand side will be 2C1. Only 2C1. That is what we have started here. What is the procedure of partial fraction? What is the procedure of partial fraction? We multiply this term and put s equals to minus 1. Here what is the partial fraction? This with respect to the root s plus 1. So what we have to do? S equals to minus 1. So that is what we are putting in order to find out C1, C2, C3. So how exactly? That is what I am saying. So that is why we have multiplied. When we find out C3, we have multiplied this entire equation by s plus 1. So we had s plus 1 in the numerator here, s plus 1 numerator here, isn't it? And we have obtained C3 directly. Correct. But when we wanted to find out C1 and C2, what we have done? We have differentiated this equation. So this term gone, and the only term then non-zero term remaining is if you put s equals to minus 1. Again we differentiate one more time and put s equals to minus 1. This entire term goes, and the only term remaining is 2c1. So that's how we obtain C1, C2, C3. Whenever we are having a multiple root, a slightly modified procedure we have to follow. Otherwise, we will not be able to get the mark. Okay. All right. So in this case, again C1 comes out to be 1, and if you put C1, C2, C3, so C1 is 1, C2 is minus 1, C3 is 1, and C4 is minus 1. If you put this C1, C2, C3, C4 in this particular equation, the equation we are expected to get is this. This is the equation we have. Now this equation is slightly different equation compared to the equation which we get when we are having real and distinct root. In this case, the roots are real, but they are not distinct. They are not distinct. So whenever we do not have a distinct root, you can see that we are getting the exponential behavior, e raised to the power minus t is there, which is signifying that the behavior of the output is exponential, but this additional term is coming into the picture. 1 minus t plus 1 by 2 t square. And this additional term is very, very important. You will see that this additional term can make your response unstable very often. Okay. And we will come back to this point. Again, I am not going to derive this again and again. I am not going to derive this again and again. Whenever we will have a multiple root, I will directly refer to this term. I will directly refer to this term, and I will tell that this additional term is going to come in the picture, and how this additional term is going to make your life difficult when you are trying to control your system. Okay, is it clear to everyone? Is it clear to everyone? Yes, no. So why I am saying that this term can make the system response unstable? Anyone? Can you figure out why I am saying? Just by looking at this particular response, why I am saying that? Okay, t tends to infinity, this term can be connected. Yes, right. So when my response is becoming infinite, is what? My response is continuously increasing. And when the system is stable when my response is bounded, it is not becoming infinite. Remember, what is the definition of stability we have defined? The definition of the stability is if the response is bounded for a bounded input, then my response is stable. But when my response is unbounded for a bounded input, then my response is unstable. In this case, this additional term can make your response unbounded because t term is there. When you take t tends to infinity, this entire term may become infinite. Is it clear? Is it clear as to? Very clear? Okay, so in this case it is not going to become infinite. Why? Because when t tends to infinity, what this term is going to be? 0. So this will get cancelled out. Okay, this will get cancelled out. But let us imagine that your roots are exactly at the origin. If your roots are exactly at the origin, what it means? It means that this e raised to the power minus t term is not there. That is what it means. Remember, this term is coming from where? S plus 1 is there. That 1 is leading to this e raised to the power minus t. But let's say if I have only S cube here, then I will not have this e raised to the power minus 3 term here at all, and in that case my response is going to become unstable. Okay, so this particular term can make your system unstable. Is it clear to you? Okay. Alright. Now let's combine all these concepts which we have studied so far. Remember, we have still not started the process control, formal process control. We have not started it. We are only looking at some basic concepts in bits and parts here and there, and we will be connecting these dots as we go ahead. Okay. So again, coming back to the same system. This particular system we have studied so many times. There is a circuit, isn't it? Input is Fi and Pi. We are assuming that the inlet flow rate is constant. So if the inlet flow rate is constant, that means the height of the liquid in the tank is not going to vary. So that means the first differential equation which gives me A dS by dt equals to Fi minus F. That particular differential equation is not required. I will be only looking at controlling the temperature. So when I take the case when Fi is not varying, Fi is exactly same as its steady state value, isn't it? In that case, the only differential equation I will be having is to maintain the temperature inside the tank, isn't it? Correct. So how we are performing that? We are measuring the temperature. That measured temperature is compared with PS, and that will give you the error. And based on the error, the steam flow rate will be modulated, and based on that, the temperature will be maintained inside the turtle. Now, why Laplace transform? Laplace transform because it enables you converting your differential equations into algebraic equations, and typically you have coupled differential equations. So if you apply the Laplace transform, you get coupled algebraic equations, and coupled algebraic equations can be solved easily compared to coupled equations. That is the reason why we use the Laplace transform. Another important aspect why Laplace transform, because you will see that for this particular system we can obtain the solution by inverting or by solving the linear differential equation, isn't it? We have obtained the linear differential equation we have obtained earlier, isn't it? dt by dt plus c, isn't it? Will be given as 1 by tau Ti plus 1 by tau Ti plus k divided by tau Fst. That is what the equation we have obtained. I can go. This is the equation we have obtained. This is the linear differential equation we have obtained, correct? For the same thing. How we have obtained the solution of this equation? The solution of linear differential equation can be obtained by using this particular formula, isn't it? By using the method of integrating factor, correct? So the solution comes out to be this. P dash t is given as e raised to the power minus alpha t, integral 0 to t e raised to the power alpha t, 1 by tau Pi dash plus k Fst dash dt, and this entire integral we have to perform. If I wanted to represent this in terms of the block diagram, I can represent using this block diagram. I have explained at that time why block diagram, because typically when we perform the process control, we have hardware units, and these hardware units are performing the task for you. For instance, there will be a hardware unit that will be performing integration. There will be a hardware unit which will be combining these two signals. Isn't it? Remember, in this case, these two signals are added. This signal is multiplied by 1 by tau, and this signal is multiplied by k, and both the signals are added here. Isn't it? So if you represent your entire system in terms of a block diagram, that also gives you a information how you can use the hardware units to combine it. Okay. That is the reason why we are representing it in terms of the block. Now, the point I wanted to appreciate here is this particular block diagram is slightly more complicated. But if you use the Laplace transform, you will see that this particular block diagram, which looks very complicated here, even gets simplified further. Okay, that is what we are trying to see. And we will see, for the same system, we will see how this particular block diagram is getting simplified. अभी तक तो प्रोसेस कंट्रोल स्टार्ट ही नहीं हुआ है, and I can see that so many people are disinterested. We have not even started. Okay. So many people are, kind of sleeping in the class. They are not at all interested. They are coming to the class only because there is attendance compulsory, isn't it? Otherwise, if I remove that, I will see only 2 or 3 students coming to the class. And in fact, I have seen this situation earlier. I used to teach transfer earlier, isn't it? And I have taken a class with 2 students. Out of 180, only 2 students came. And that is the reason why I made it compulsory. Because I require that inspiration. Whether you want to get it or not, I don't care that, isn't it? Otherwise, you will lose the interest over the period. I have seen very good teachers in the system over the period, they have not very much. Finally, because students are not. If you are, behave like this, then there is no end. I will take the classes and I will do all these things. I have done several times. And so many times I have done, I remember each and every term. Okay. More or less I know everything in this course. I am telling you, because this course I have done on the blackboard 5 times. So all the equations I remember by. There is nothing I will do. Okay. But there is all the things for you. It is not about whether you are interested in chemical engineering or not. Okay. Whatever जो बोलते हैं ज्ञान अगर मिल रहा है ना, फ्री में तो ले जाते हैं कहीं से भी, क्योंकि कहाँ यूज होगा you never know. Isn't it? तो कहीं से भी मिले ले लो. Don't be disinterested in something which is given free of. I don't know why this behavior I see in recent time. देखो जो विद्या है उसका दान होता है, वो दिया नहीं है, वो मतलब आपने खरीदा नहीं, उसका दान है. अगर आप ग्रेसियसली उसको नहीं लोगे ना तो मिलेगा नहीं, काम ही नहीं है. आप चाहे कुछ भी कर लो, यहाँ से टॉप कर दो, कुछ भी कर लो, you will find that you are getting used anyway. You have that feeling when you are coming to the class. Otherwise, it is always. मेरे लिए कुछ नया नहीं है. I will come every day, whether you are interested, not interested. I will still do the class. And as I said, whether you like it or don't like it, I don't care. Whatever duties are given to me by IIT, I will definitely do. In this journey, if you become the part of this entire process, then it is good. If not, it is entirely up to you. Okay. So this is a very new concept of bunking the classes. I have never bunked the class. Never bunked the class. Whether I like a teacher or don't like a teacher, still I have not bunked the class. We usually, have that bet that this class will be enough okay. That type of thing we used to have, but still I have never bunked the class. Now I see that people are not coming to the class, they are only in these hostel facilities or watching movies. And I can tell you, this is what the situation is. Over the period, your hostel allotment will be linked to your attendance. And it will happen. It is already linked. It is going to become more. Okay. So see, it's a game between system and surrounding. If you play in some way, surrounding is also going to play. Isn't it? Correct. Don't expect that the surrounding will remain as it is. It is not like that. Correct. अब ये आप पे है कि how you wanted to play. Correct. Okay, so in the same system we are saying that the use of Laplace transform will give you a simpler block diagram compared to the block diagram we are expected to get in time domain. Okay, that is what we are seeing. Now for this particular system, this is the equation. V dt by dt is given as Fi Ti minus C plus Q by rho Cp, isn't it? This is the equation. The Q we can substitute by lambda into Fsc. We are assuming that the steam is saturated. We are assuming that the steam is saturated. So amount of heat given will be related to the latent heat of vaporization. So latent heat in this case is lambda. Latent heat into flow rate, that will give you the amount of heat. So Q will be given as lambda Fsc divided by rho Cp. If I rearrange the term, what we are going to get? If we rearrange the term, this V, if I divide this Fi, V by Fi is tau P. V by Fi is tau P. Tau P we have not defined it. We are going to define later. Tau P for a time being, assume that this tau P is the time constant of the process. Tau P is the time constant of the process. Okay, that is why the subscript P is given there. It's a time constant of the process. We are going to define this particular term little bit in more detail as we go ahead. There is a physical significance of this time constant. It's not we have taken only for sake of taking it. There is a reason why we have taken it. Okay. So if we divide this entire equation by Fi, this V by Fi becomes time constant tau P. The equation becomes tau P dt by dt plus C equals to Ti plus lambda by rho Cp into Fi. And this entire term we are representing as Kp. This Kp is nothing but what? It is nothing but the process gain. This is referred as process gain. Okay, process gain related with the manipulated variable. In this case, remember Fsc is a manipulated variable. So the process gain associated with the manipulated variable is always represented as Kp. And there is just one, but just for a sake of general representation, we are representing here Kd. Okay, so Kd into tau I plus Kp into Fsc. So Kd is nothing but what? Kd is nothing but process gain associated with the disturbance variable. Okay, so all these terms which I am defining here, these are important because later on we are going to represent the process directly in terms of these. Time constant, process gain related to the manipulated variable, process gain related to the disturbance variable. Okay, so you can see that the left hand side here is having the output variable, whereas right hand side is having only the input variable. What are the input variables in this case? Ti, which is nothing but the inlet temperature, isn't it? And Fsc, which is nothing but manipulated variable. Okay, so this is the equation which we have obtained. Now, if we represent this particular equation in terms of steady state, so at steady state, this term is going to become 0 and all the variables are going to become steady state values. So T will become Ts, Ti will become Tis, Fsc will become Fsc. If I subtract this steady state equation from this original equation, I am going to get the equation in a deviation form. So all the variables in a deviation form are represented by dash. So when I am representing T dash, it is nothing but T minus Ts. Okay. So this is the equation we have obtained. If I wanted to solve this particular equation in a time domain, this particular equation is a linear differential equation. Solution of linear differential equation we can directly get, isn't it? This is the linear differential equation. I can get the solution of this linear differential equation with the same formula which we have studied earlier, isn't it? So this is how I am going to get the solution of linear differential equation. Now the only difference in this equation and the equation which I have shown earlier, the variables I have changed. There the variables I had alpha, I had capital K, isn't it? In this case, I have introduced three new variables, tau p, kp and kd. Tau p is the time constant of the process, kp is the process gain associated with the manipulated variable, and Kd is the process gain associated with the disturbance variable. Okay, that is why we have represented this entire equation in terms of these three variables, because later on we will be representing our process directly in terms of these three variables. Directly in terms of these three variables. Okay, I can go back and explain that. So I can write down the process in terms of these three variables directly like this, isn't it? Isn't it? This entire equation is coming from the differential equation, isn't it? Correct or not? And how we are representing our process in terms of equations. In terms of equations. Okay. So this is the solution which we have obtained, and with this solution the block diagram will represent like this. Now this particular block diagram is definitely complicated, isn't it? It's not easy. Correct. Let's come back. This is the solution in time domain. This is the solution in time domain. Let's obtain the solution in S domain. Let's apply the Laplace transform and see whether it is going to simplify or not. So this is the equation. This is the equation we had, isn't it? Let's apply the Laplace transform. If we apply the Laplace transform, what we are going to get? What is the Laplace transform of this? Tau p into s t dash s minus t dash 0. But t dash 0 is 0 because t dash is given in a deviation form. So what will be the initial value? If you take the t dash 0, that is going to be 0. That is going to be 0, isn't it? Because that is ts minus ts, isn't it? So only term I will have is tau p s t dash s, and the Laplace transform of this will be t dash s. Laplace transform of right hand side will be kd ti dash s plus kp fst dash s. I can rearrange this entire equation. See what I am interested in. I am interested in output. What is the output variable here? T dash is the output variable. So I can represent this T dash in terms of these two input variables. So T dash can be given as kd divided by, I can take this T dash common here. So what I will be having? Tau p s plus 1. Isn't it? And that if I take it on the right hand side, that becomes 1 upon tau p s plus 1. So it becomes T dash s is kd ti dash s divided by tau p s plus 1 plus kp fst dash s divided by tau p s plus 1. Now this equation is an interesting equation. This particular equation we are going to write again and again. Whenever I am looking at first order process. Remember in this case, the differential equation we started with was first order differential equation. So whenever I have a first order differential equation, I am likely to get the equation like this. Isn't it? So whenever I have a term 1 upon tau p s plus 1 multiplied to some input, that signifies that this particular equation is actually originated from first order differential equation. Isn't it? So this power of s, here in this case, what is the power of s? What is the degree of s? Only 1. So this degree of s defines what equation we have used. In this case, the degree of this s is 1. So that clearly indicates that this equation is actually coming from first order differential equation. Let's say if I would have had s square here in the denominator, then that would have given me the insight that this equation is actually originated from second order differential equation. So just by looking at the degree of s, you can figure out whether this particular equation is coming from first order differential equation or a second order differential equation or some other higher order differential equation. You can figure out that. Okay, is it clear? So once we have obtained this particular equation, I can represent this equation again in a simpler form. So this term kd divided by tau p s plus 1, that we represent as gd, and the other term kp divided by tau p s plus 1, that we can represent as gp. Here gd is nothing but the transfer function of the process with respect to the disturbance variable or load variable, whereas gp is nothing but the transfer function of the process with respect to the manipulated variable. Okay. Now once we have written this GD, TIS and GP, FSCS, this particular equation I can generalize. So my generalized equation is given as y dash s is given as GD into V dash s plus GP into M dash S, where M dash S is nothing but the manipulated variable, this is the disturbance variable. Now this is the generalized equation I am going to use every time whenever I have to go back to the first order process. Whenever I wanted to take the first order process into the consideration, I am going to write this equation directly. I am not going to derive it again and again. Isn't it? This is what we are going to get when the first order differential equation is there. Okay? Is it clear to everyone? Once we have obtained this, now let's look at the block diagram. Block diagram became extremely simplified. See, this term TIS is multiplied to ZD, TIS is multiplied to ZD, and FST is multiplied to this, isn't it? And both these signals are added, and addition of these two signals is going to give me T dash S. That is what we have obtained. Only these two blocks are added here, and that gives me the output. So clearly this particular block diagram is much more easier, much more simpler compared to the block diagram which we have seen earlier. Okay. Now this brings me to another important concept. Remember I said transfer function. GD is a transfer function of the process with respect to disturbance variable, and GP is the transfer function of the process with respect to the manipulated variable. Now what is this transfer function is? Transfer function is in this course, so now we are actually starting the process control. Okay, so you will see that in the process control the term which is most regularly used is a transfer function. What is transfer function? Transfer function is nothing but the equation which gives you the relations between input with output. How my output is going to vary if there is a change in the input. This relation, the equation which is establishing this relation is referred as a transfer function. Formally the definition of the transfer function is this: Laplace transform of output in a deviation form divided by Laplace transform of input in a deviation form. This word deviation is very, very important. This word deviation is very important. So Laplace transform of output in a deviation form divided by Laplace transform of input in a deviation form, that is defined as a transfer function. So transfer function is relating output Ys to the input f of s. Okay. So if I wanted to find out Ys, what Ys is? Ys is given as g of s into f of s. You can see that in terms of transfer function how the process is represented. Actually in a time domain f of t is the input, yt is the output. If I wanted to represent this in terms of the transfer function, I have to represent this as f of s. Here we will have g of s and y of s. Output is y of s. Okay. You can represent input and output not just for single input, single output system. You can represent that for multiple input, multiple output. This is multiple input, single output. Isn't it? You can do that easily. There is no problem. And once we have written this equation, remember actually even though this particular equation is giving me how my output is related to the input in a Laplace domain, but actually I am interested in time domain. Actually I am interested in time domain, how my output variable is going to vary with respect to time. So what we have to do, we have to invert this equation into time domain. We have to take the inverse Laplace transform of right hand side, and that will give me y of t. That will give me y of t. Okay. Very often the process system we are looking at, these systems are non-linear in nature. So whenever the equations are non-linear, the first step what you have to do is, first you have to linearize it. First you linearize it and then you apply this Laplace transform of the output in a deviation form, Laplace transform of the input in a deviation form. If you take the ratio of that, that will give you the transfer function. That will give you the transfer. Okay? Is it clear to everyone? Yes, no? Is it becoming too complex? It's not at all complex. We have not even started. We have not even started. We are only looking at Laplace transform which we have done in your JEE days. No? It was not there in JEE. In MY or M2, isn't it? First year you have done Laplace transform. How seriously you have done, that is question mark. But at least done somewhere, isn't it? Correct. Now very often I see that people lose the interest just after the first year because they don't get computer science. Computer science is not everything. So see, I am chemical engineer and all my research in the computer science. It is based on your choice, how you wanted to pursue your interest, isn't it? It's not about the brand. It's not about the brand. Even if you are in the chemical engineering or even in biochemical engineering, I can say that with surety that you can pursue your interest if you are interested in something. So don't get disheartened if you don't get the computer science. It's not the entire world. Alright. Where we are? So one more. Do we stop here or continue? We have to complete 23 chapters. Okay? We have to complete 23 chapters. And don't be in the wrong impression that I am doing lot of material. It's not lot of material. I am doing only that much material which is there in the GATE syllabus. So you are expected to study that. I am not going beyond that. Okay. Alright? So very often I see that comment that syllabus is too much. Syllabus is not too much bad. All the 7 or 8 chapters are the introduction, so that you can prepare yourself for the subject. Okay? So we stop here and we will continue from this.
सबको